Why haven't we talked about particles down here at the bottom? Or test charge down here? What would have to happen if the particle's location were down here? Or over here, over here, over here?
Have to work with the angles of the charge?
Yeah, this would be at an angle, right? You'd have to use trigonometry to do that. You'd have to use your right triangle trig in order to calculate if the test charge were here. But if it's here, or here, or here, or somewhere along the line between these two particles, the line between two particles is literally the line drawn from center to center. If the test location that we're interested in is anywhere along this line, we're fine. It could also be out here. So let's look at a location out here on the far right. Let's say that this is our location of interest. Okay, all the way over here. And we know that the location from the center of the particle on the right is an additional, let's say, 0.07 meters. So this is 0.2 meters to the center. From the center out to where the field is, it's 0.07 meters. So we're looking at 7 centimeters. And the question says, determine the electric field intensity at that location. Determine the electric field intensity at that location. We have to consider the fact that you have two sources. Now, those sources themselves would be repelling one another. But let's say that they're fixed in space. Okay, they're stationary. This source over here would have a huge impact on this chart, on this location, because it's very close. This source is extremely far compared to the other one. It's almost 4 times as far. So as a result, the intensity from the field on the left is not going to be nearly as much as the one on the right. Now we have to know what the actual field itself is. So let's say that the one on the left is, we'll make it a small number, so like 7 nanocoulombs. And the one on the right is, let's say, 6 nanocoulombs. So remember, nano is times 10 to the what? Nano times 10 to the...
-6.
No, but put those two together. -9. She said 9, you said -6. -9.
Oh,
Micro, 10 to the -6. Nano, 10 to the -9. So that's what we're looking at for these two charges here. So if we want to figure out what the electric field intensity is here, not the force felt, not the force, but the electric field intensity, what is our formula for this? For electric field intensity, what formula are we going to use? Katie? Okay, E equals KCQ over R squared. KC, what is KC?
0.99 times 10 to the...
But what is it physically? It's a constant. It's on your table. You don't have to memorize it, okay? But 9 times 10 to the 9, you could remember if you want to, but it's on the bottom of your formula sheet. So constant, Q. Q is what? Physically, what is it? The charge on the particle, or the source. In this case, we have two sources, depends on which one we're looking at. And R is the distance between the centers of them. So we have to consider the fact that both of these sources provide some sort of intensity at that location. In class, we've been looking at a location here, right? Somewhere in between. We did one in the center. I think for your problem set, number 38 was the one that a few of you asked about. I think it was also, was it in the center as well or no? Who just did number 38? Dro, didn't you just do number 38?
Yeah.
Was the location in the midpoint between the sources?
Yeah.
Okay. So it could be anywhere, obviously, right? But you have to consider the fact that each of those sources would provide some sort of motion for that particle. So if this particle over here were positive, which way would it move as a result of these sources? Which way would the particle move at the x if it were a positive test charge? Yeah, away or to the right, let's say. Again, if there was a proton right here, a proton would move to the right because of the opposite charge, the same charges would have forces that would repel. But we're not looking for the force, we're looking for the electric field. So we can go ahead and calculate the electric field acting at this location using superposition. Remember that term superposition from class we talked about? It just means add together the two electric fields independently to get the overall electric field. So here we can go ahead and take a look. We've got 7 and 6 nanocoulombs. So the electric field from the first one is going to be 9 times 10 to the 9. Now, I'm going to put everything in base units, so I'm not going to provide units, so make sure you are in units correctly. What would Q be? For the one on the far left, what was Q? 7 nanocoulombs. But how do I write nanocoulombs? How do I write nanocoulombs? 10 to the negative? Somebody said it. Negative 9, okay? All over the distance between them squared. Well, if I go back up to the diagram and take a look at that, what's the distance between the source on the left and the far x on the far right? What's the overall distance between them?
2.07. Oh no, I thought that was 2 meters.
It's 0.2 meters.
It would be 0.207.
Not 207. Come on, Drew. The distance from center of the left source to the x on the far right? 0.27. 0.27. Okay, that would be the electric field intensity from the first source. From the second source, how would it change? What would E2 be? What would be the changes we'd have to make? Yeah,
It
go.
would just be 0.07.
Okay, 0.07 is the distance from there. What's the charge? The other one was it 6? 6, right? What do we get for each value? What do we get for each value when we calculate these? Somebody check, please. I'm going to also talk about the units for a second. Why are the units newtons per coulomb? Why are the units newtons per coulomb? You know what?
Isn't it because it's the amount of force on the charge
You're on the right track. The amount of force, not on the charge, but per coulomb of the test charge, really. Think about the electric force. The electric force formula, I'll draw it in up here. What do you got, Nat? Yeah. 20.4?
Yeah.
And the second one?
Oh, that was his one.
That was the second one.
Yeah, sorry, I didn't see. I was looking at the top.
For the second one? Uh-oh. What'd you get? For the second one? Which one is it, guys? You got Natalie got. Katie, check yours. I got 3 with that answer, so check yours.
One is 864.2.
864.2? So the sum of those two numbers will give me the overall electric field. Why is that? Why is it the sum of those two numbers gives me the total electric field? No? Joe? Sorry, God, you were going to talk and then he raised his hand.
Oh, it's because it's negative. It's positive.
No, they're not both. They're both positive. Yeah. Why didn't we subtract them? Because on number 38 in your textbook, you just did. Didn't you subtract them?
Yeah.
Because the point we were looking at, here were the two positive charges. The point was in the middle, right? So both of those positive sources pushed against each other. But now, positive source, location of testing out here. Which way does this source push it? To the right. Which way does this source push it? To the right. Both of these sources are going to push the test charge to the right. So they're both positive numbers. So we're going to sum these together now. Do you see why I changed up this problem a little bit so you guys can see the difference? If the x was in between and we were looking for a location at like a midpoint, and there were two positive sources, they'd be pushing against each other. So you'd have to subtract the two or add one to the negative of the other. Okay? So what are we going to get? 11,884.6. Okay, 11,884.6. Now, the answer that we get is in newtons per coulomb. There's a really easy reason or easy way to remember the units, because a lot of people forget these units. Think back to this formula. Take a look up, please. No matter where you are, stop. Take a look up. Look at this formula from earlier in the year. Okay, so this formula is solving for what? What does FE stand for? What does FE stand for, class? Electric force. So what are the units of this? Force. Newtons. Everybody, whenever you hear force, it does not matter. Centripetal force, tangential force, it does not matter what force you're looking at. The net force in newtons, right? Newtons. So this is newtons. Well, look at this formula on the left. How do they differ? How does this formula here, written in white, for the electric field intensity, how is this different from this one? What's the difference? Yeah, you're missing Q here, right? There's only one Q. Here, Q1, Q2. Here, just Q. So if you're missing Q, you're missing the units from Q. What are the units from Q? What are the units from Q? Okay, it can't be just Anthony, come on. The units from Q is coulombs. We should all be able to answer that right away. Charge is measured in coulombs. So if you're missing a Q here, it means that it's the same units as this, which is newtons. But since you're missing coulombs, newtons per coulomb. Newtons per coulomb. So you're missing coulombs, so coulombs are in the denominator. Again, the units of this would be newtons. The units of this is newtons per coulomb because you're missing Q. It might not work for you to memorize it if you don't understand what I'm getting at or what I'm talking about specifically there. Okay, but the idea is that you're missing Q, which means you're missing a coulomb charge. So you can't have it. It's not just newtons. It's newtons divided by coulombs. It was 17.3. That's a good example of one you could imagine for like some sort of an assessment for 17.3. Not really much more difficult. It could be between the two charges. You could have a positive and a negative and a positive, a negative and a negative, a positive and a positive. You could have all those possible arrangements of sources, right? If they're both negative, right? If they're both negative, it's like a tug of war. This one wants to pull it toward it. This one wants to pull it toward it, so you'd be pulling apart again if it was in the middle, right? But if both were negative and the object test charge was out here, it would be being pulled toward this one. It would also be being pulled toward this one because they're both negative and the positive test source is out here. If it's a positive and a negative, the field lines go away from the positive toward the negative, so it would both be acting toward the right if it was in the middle. It really depends on where that test is. So when you guys want to test yourself, pick two sources, pick a location, either somewhere out here, in between, or out here. It doesn't matter. And make those sources either positive, negative, negative, positive, negative, negative, or positive, positive, and try those examples out and see what you get for your answers. But think about what it would cause a proton to do before you start the problem. You know, depending on where that X is, which way would a proton move is the question you're asking yourself. Other math questions specifically. We good on the other stuff? Calculating power, the cost for power, or the cost for your energy bill. Okay with that? Did I give you one on the problem set for that?
Yeah.
Why would you do a practice of that though?
You what?
Let's do a practice of that one.
You want to do what?
Wait, does this involve resistance?
This involves power. Resistance could be involved. You want me to involve resistance? I can make it involved. Sure. So let's say that. All right. The resistance of a toaster is 100 ohms. Like a toaster, you know. Toaster oven. Actually, no, a regular toaster, not a toaster oven, is 100 ohms. And the current, let's do voltage. Supplied is 120 volts. If the toaster is on for 6 minutes, is it though? I guess it is, right?
No, that is a
You're just
long
gonna get
one. It's
burnt
like
toast.
2 or 3 minutes essays.
I know, but 6 is a fraction of 60 that works very easily.
I feel like that'd be really burnt, so
six
just a
minutes.
fire hazard.
All right.
If you want to
I'm trying to make the numbers work better. 6 out of 60.
Which one burnt?
3.
Make it something
Reasonable? 3. All right.
Unless you're baking like mini.
I don't know. This morning, I've been waiting for 4 minutes this
How
morning.
many pieces are
A sesame bagel, it was
I
perfect.
feel like eating hard.
It wasn't that, because you know why? The toaster itself, I did it in the toaster oven actually. That takes a little while to heat up. Maybe that's why. Whatever. So 3 minutes. If the toaster's on for 3 minutes, determine the energy consumed in kilowatt hours. Determine the energy consumed in kilowatt hours. Once we know the price per kilowatt hour, we can determine the cost to operate a functional toaster. All right, so that's what we know so far.
Wait, do we have to convert minutes to hours?
We probably do. That's a really good point. Because you see that you're going to look for kilowatt hours, right? And this is in minutes, so I'd probably start by doing that first. That's a good idea. So let's list our knowns and write down what we can do. So we know that the resistance is how much?
100.
Units?
Ohms.
Ohms. Okay, the symbol is omega, but it's ohms, like Ohm's law. The voltage supplied, that's the obvious one always, right? Because the units are the same. How much? Okay, remember the units are the same as the variable there. And then finally the time it's on for is 3 minutes.
Which is 0.05
How did you get that?
divided.
Yeah. Okay, 3 minutes, obviously, times 60 minutes per 1 hour, which is 0.05 hours. Okay, we're going to cancel. So we're going to use these 3 values right here. Okay, 1, 2, 3. Now, what do I need to figure out before I can do this problem? I'm trying to find the amount of energy used. Energy used. I can't use kinetic energy formulas. I can't use potential energy. Where else is energy? It's in one other formula. One other formula.
Is it work?
It's work. Energy is work. And where's the work formula? How does that relate to what we're doing here?
It's force equals distance.
You're just guessing now? Emma?
P equals W over T.
Okay, P equals W over T, or P equals energy over time. The rate of change of energy is power. Okay, remember, power is measured in watts. Watts is joules per second. So joules, second. Now, the problem is, I don't have the amount of joules, do I? I've got nothing about energy here. But I do know something about power. If I know power and time, I can find energy. I can calculate the power consumption. What formulas do I have to choose from for power consumption? There are 3 formulas. Which one will you choose for this problem?
It's going to be P equals V squared over, actually, over R.
P P equals, go ahead.
V squared over R.
V squared over R. Why do you choose that? Somebody else, why do you, I know you don't. Why do you choose that? Why do you choose V squared over R? Why not P equals IV? Why not P equals I squared R? How come it's P equals V squared over R? You don't know I. The current is unknown. If you don't know the current, it doesn't make sense to solve for the current and then use it again. That would be an extra step. So since you don't know the current, oops, don't use the current itself. Okay, don't use the current because you don't know the current. So as a result, we're going to use, again, P equals V squared over R. V squared is going to be 120 volts. Squared over the resistance of R. How much power do we generate here? 144 watts. Yes? Should work, that's right. This is 12 squared really, and then that's another 1 squared there. The 2 zeros are going to cancel with the 2 zeros, make it 144. Can we keep that? Is that okay? Watts? Are we good at keeping in watts?
We're using kilowatts.
What is the energy unit in?
Kilowatts.
Kilowatt hours. Energy was asked to be solved for in this problem in kilowatt hours because your energy bill you get is like 10 cents per kilowatt hour as a rating. So it's got to be kilowatt hour. So to make it kilowatt hour, let's make this power into kilowatts. What is that as a kilowatt?
You multiply by 1,000. Or you divide it.
Divide by 1,000.
0.1.
Okay? Three spots, kilowatts. You could change with the dimensional analysis, kind of like we did up here. The minutes cancel with minutes. You could put, right, obviously this is watts. You could say 1,000 watts per 1 kilowatt. Watts cancel. You get 144 over 1,000. So 0.144 kilowatts is the amount of power that this toaster draws. Very, very, very low consumption of power. Okay, 0.144 kilowatts, that's the amount of power. Now from this formula here, oops. From this formula right here, we can go ahead and take the power, plug the power in, take the time, plug the time in here to get the energy. So we've got, again, the time it takes, the actual amount of power plugged in to give us the energy. It's a very, very, very small amount of energy. How much energy would it consume? In kilowatt hours, what would be the consumption here? Emma, go ahead. Careful. Because that got bigger, right? It can't get bigger. It's got to get smaller. 0072. Is that right? 0072?
Yeah.
Yes? Okay. We're going to take that answer if we want to figure out the cost that we pay our electric bill and multiply it by our rate. So if it costs you 25 cents per kilowatt hour, and that's what Con Edison is making you pay your energy bill to the electric company usually. So you pay 25 cents per kilowatt hour, you would just cut this in a quarter. Okay, a quarter of that would be 18, so 0.0018. So it would be less than a penny to run that toaster oven, or that toaster, for the 3 minutes that you ran it. Now, let's talk about realistic nature of this problem. First. The actual amount of resistance would probably be less than 100 ohms. I'll just pick that number to be roundabout, which would increase the amount of power consumed, which would mean it would take more energy. Second, the resistance of a toaster is not going to be a linear thing. It's not going to be the same resistance the whole time. The resistance would really actually vary. It would take a lot of energy in the beginning just to get that toaster heated up. Then maintaining it would take less, and then as it cools down, it would still be giving off. Well, once you turn it off, it would stop supplying power. Okay, but on the startup and the maintenance, you would have a variable resistance. It wouldn't be the same resistance the entire time. Okay, so it could fluctuate. So this number could be a little bit greater as a result of the fact that the actual resistance would really vary. And then again, 3 minutes I guess is pretty reasonable for a toaster. Toasters are made to consume very little energy. Okay, to consume very little energy, we're going to see a very small amount there. So at the end, if you ever want to find cost, remember, you take the cost, or you take the energy, and you multiply it by the rate. Okay, and the units, just so you know, units are going to be dollars equals, and energy is in what? Kilowatt hours times dollars per kilowatt hour. Okay, so again, cancel, dollars equals dollars. You can see that it's the right formula. Do I give this on your formula sheet? I don't think I do. Take a quick look, open your formula sheet, let me know. I don't think I put this here because this is like, you learn this in 9th grade math. If you want to know how much cost you're going to pay for something, and you have the energy, you need to know the dollars per energy.
You put cost equals energy times rate.
Okay, so I put this on here?
Yeah.
That was nice of me. I don't know, I should check. I don't think they're on the laminated one, so I should let you know one way or the other. So you know for the test. Aside from this, the rest of the math in this test is pretty straightforward. I think there's not much more to it. These are the 2 topics you can definitely expect problems on. Joe.
Is there a lot more conceptual than the math on the actual test?
I mean, some of the stuff might show up like we didn't use V equals IR, Ohm's law, just now. We didn't use the other formulas for power just now, IV.
Like multiple choice.
Or those could be like even like things where, multiple choice where I say, as the voltage goes up, what happens to the power? You should know that it goes up. It's in the numerator. P equals IV or P equals V squared over R. Either way, as voltage goes up, power goes up. As the current goes up, the power goes up. You know what I mean? So you have to consider that kind of stuff. And depending on the scenario, I'll give you more. And then, yeah, the part 2 stuff, the middle stuff, you can expect some conceptual stuff to come up there in the middle. I'm trying to think of what other conceptual. There's a lot more we're going to talk about tomorrow. But for the math part, this is really the main 2 problems you want to be considering. 19.1, was there any math? I don't think. I think I said I equals delta Q over delta T, but we really haven't done much with that topic about current there. In chapter 20 later on, there's a lot of math. In 20-2 and 20-3, there's a ton. So in 20-1, it was mainly conceptual, so we didn't have to worry about that. But some of you I know do better with math, so you'll see that on the next test for sure. All right, I'll stop at this point from here.